This is a typical production line in a factory. In fact, it's a Japanese factory in England manufacturing television sets, which was the subject of a report in the BBC series The Risk Business. The programme compared Japanese with British-owned firms, and what interests us is the jobs policy the reporters found in operation in the factory.
The production line could come to a halt if just one girl is absent. So each person is expected to be able to do at least 2 jobs, and the floaters are skilled in as many as 10.
The motives for diversifying skills are apparent enough, whether to cover illness or to give variety. But we may surmise that not everyone can do quite every job. And from this assumption, we set up an interesting question, which might just test the imaginative manager. The question we want to pose is, how many ways are there of dividing up the jobs in such a situation? And the interest in this is that it turns out to be an example of a much broader type of problem, as we shall show in this programme. So let's look at the jobs problem more closely.
Well, just to be sure we know what this problem is, I've got a diagrammatic form here. I've got 5 rows corresponding to the 5 jobs, and I've got 5 columns corresponding to the 5 people. And in each column, I have 3 black squares, and those are the 3 jobs that particular person is skilled at. Now, it's easy to find a way of allocating people to jobs. For example, going by column, you can take the 2nd job, the 3rd, the 4th, the 5th, and back up to number 1. And I'm sure you can find lots of other ways. But that, in fact, is the question. Just how many ways are there of assigning the people to the jobs? That's the problem we're going to be looking at.
We shall see that several problems turn out to be essentially the same. That is, they have the same model. So what we're going to do today is to show you the mathematical techniques by means of which all these problems can be solved. We're going to approach the mathematics by looking at some problems that we find on the chessboard. And we're going to be concerned particularly with this piece, the castle, or rook, as it's usually known. The rook moves on the chessboard any number of squares up and down a column or across a row, so that if there's a piece of a different colour on the same column as the rook is attacking that piece. If the enemy piece is another rook, the rooks are attacking each other. Let's just clear these other pieces out of the way. We can now ask, how many ways are there of putting these 2 rooks on the chessboard so that neither of them is attacking the other? Wherever I place the white rook, it attacks the other 7 squares in the same column and the other 7 squares in the same row. So I can't put the black rook there. And I can't put the black rook on the same square as the white rook. So that's 15 squares I can't put it on, and that leaves 49 other squares which are safe from attack. So, for each of the 64 squares on which I can place the white rook, there are 49 possibilities for the black rook. So the total number of possibilities is 64 times 49. That's 3136. Now, for each one of those solutions, there's another solution involving the same 2 squares on the chessboard, but with the rooks reversed. So, if I ignored the colours of the rooks, these 2 solutions would be the same, and I'd only have half as many possibilities altogether. That's 1568. Well, having modified the problem so that we're ignoring the colour of the rooks, I can now extend it. How many ways are there of placing 3 rooks on the chessboard so that none of them are in the same row or column? How many ways are there of placing 4 rooks, and so on? And I can generalise this to ask, how many ways are there of placing k rooks on the chessboard so that no 2 rooks are in the same row or the same column?
Well, I'm going to denote the solution to this general problem by r suffix k. And I can then form a generating function, rx is equal to r0 plus r1x plus r2x squared, and so on. Now, you'll notice I stop at the term with r8. The reason for this is fairly obvious. You can't put more than 8 non-taking rooks on the chessboard. So this means, in fact, we've got a polynomial. We call it the rook polynomial of the chessboard. Now, in section 9.3 of the text, we found generating functions to be a very powerful tool in various enumeration problems. And rook polynomials are no exception. With their use, we're going to be able to solve a variety of problems in a variety of mathematical contexts. And this will include the jobs problem with which we started. Just let's clear up a few loose ends. Can we get some of the coefficients? Well, we know R2. It's just the number of ways of putting 2 rooks on this board, and we've seen the answer to be 1568. How about R1? How many ways can I put 1 rook on the board? Well, of course, it's just the number of squares, which is 64. Now, R0 might give you some trouble. How many ways are there of placing no rooks at all on the board? Well, the answer actually is 1. And the way to look at it is this. There's just one arrangement which hasn't got any rooks. Now, with many mathematical problems, the fun really starts when you generalize. And I'm going to generalize the idea of a rook polynomial to different boards. And I'm going to begin by thinking about n by n boards. Let me start with something simple, just this 4 by 4 board here. If you try working out its rook polynomial, the answer you'll get is this. Let me try and give you some idea of how you get this. The first term's obvious, that's just the R0. The second and third, well, it's the same kind of argument I've been through already, so I won't go through that. Now I'll just talk about the last one, this 4 factorial. Where does that come from? Well, if you're putting 4 rooks down, you see, think about it. 1 must be in each column. So what about the rows? Well, there's 4 choices for the first, 3 for the second, 2 for the third, and there's your 4 factorial. Now, at the moment, I don't have any colors. I haven't got them because they don't really matter. They don't affect rooks. But if we put the colors in again, we put the white squares back in, it enables us to look at a different problem. Suppose we consider just the white squares. We can ask how many ways there are of placing a given number of rooks on just these white squares so that no 2 rooks are in the same row and no 2 rooks are in the same column. Let's divide the white squares into 2 sets. We've colored 4 squares pink and 4 green. Can you see that each group of 4 squares has its own 2 rows and its own 2 columns, not shared by the other 4 squares? Now, the point is this. Any rooks placed on one group of 4 squares in no way affect the placing of rooks anywhere on the other 4 squares. So can we somehow use this to calculate the rook polynomial? Well, indeed we can. Let me show you how. Each group is just 4 squares. So its rook polynomial is that of a 2 by 2 board. It works out as what I call r suffix 2 of x and is equal to 1 plus 4x plus 2x squared. Now the rook polynomial of the 8 squares, both pink and green together, turns out to be equal to 1 plus 4x plus 2x squared, all squared. In other words, just the square of the rook polynomial of the 2 by 2 board. The easiest way to see this is to multiply out, like this. Look at the coefficient of x squared. Here there are 3 ways to split the 2 rooks, both on pink in 2 ways, times 1 way for no rooks on green. That's the first term in the bracket. Or we can put 1 rook on pink in 4 ways and 1 on green, also in 4 ways, giving the 4 times 4 term. Finally, we can put no rook on pink in 1 way and 2 on green in 2 ways, and that's the last term. You can work out the other coefficients by similar arguments.
Well, what does all this mean? We've got a simple instance of a useful result. If we want a rook polynomial of a set of squares which fall into 2 subsets, such that any row or column on the board has squares in it from only one of the subsets, then the rook polynomial for all the squares we're looking at is equal to the product of the rook polynomials for each of the 2 subsets. And this we call the product rule. We're going to make use of this result later, but first, let's establish a few very simple cases which we're going to need later in the program.
Here's an example of a symbolic notation we shall find extremely handy. We simply show you the set of squares whose rook polynomial we are talking about. Well, here we have just 1 square. That's easy. 1 way of placing no rooks and 1 way of placing 1 rook, so we get 1 plus x. Equally easy is r of these 2 squares. 1 way of placing no rook and 2 ways of placing 1 rook gives 1 plus 2x. Of course, there is no way of placing more than one rook, as there's only one row. But what do we mean by this? The rook polynomial of a blank board. Well, if there are no squares, there can be no rooks. But there is still the one way of arranging no rooks. So r of nothing is 1. Here's an interesting case. I'm sure you could work it out, but before things get too complicated, we need some tricks up our sleeve. And there is one we can employ here. Choose a square. Any square will do, but let's look at the top left-hand square. Now the point is this. Either we put a rook on that square, or we don't. If we don't put a rook on the chosen square, then we have just the rook polynomial of these two squares. If we do put a rook on the chosen square, then we can place no other rook in the same row or column. So we're left with just this. We actually get this equation. If you consider, for example, the coefficient of x arising from the left-hand side, this must be equal to the number of ways of putting one rook on either of these two squares, plus the number of ways of putting no rooks on the blank board. So that's why we need the x on the right-hand side. We'll come back to this later. Now, if we look at the first term only, we can apply the product rule. This gives just r of 1 square times itself. So our original equation just becomes this, which works out as 1 plus x squared plus x, or 1 plus 3x plus x squared. The coefficients of this formula tell us that we can place no rooks one way, one rook in 3 ways, and 2 rooks in 1 way. Well, we've deliberately given a roundabout way of dealing with what is a simple example. But the idea will be of great utility in more complex situations.
We've talked about the rook polynomial relating to a standard chessboard squares, but we could equally talk about the rook polynomial of any collection of squares on the board. And here, I've got a different configuration of white squares, rather fewer than before, I think. Now, finding the rook polynomial of these white squares would be very difficult without a trick or two. Well, we've already established one useful result, and we shall now establish 2 more to help us in our aim of being able to evaluate the rook polynomial for any combination of squares. So, let's set up the result we're going to need. We can use the same idea of choosing a square and then eliminating it for the case when there is no rook on that square, and then eliminating the whole row and column of that square for the case when there is a rook on the square. The equation we get is this. By the same argument as before, the rook polynomial for the original configuration is the rook polynomial with 1 square blotted out, this is the square that's winking, plus x times the rook polynomial for the configuration with the whole row and column blotted out. Notice that the x in the second term ensures that it's the coefficient of x to the k minus 1, because only k minus 1 rooks are outside the cross, which contributes to the coefficient of x to the k for the k rooks altogether in the answer. Does this equation look familiar? If you think about it, we've got here an equation relating the rook polynomial to a rook polynomial of smaller configurations. So it's a kind of recurrence relation. In fact, we're saying that the coefficient of x to the k on the left is equal to the coefficient of x to the k for the first configuration plus the coefficient of x to the k minus 1 for the second one. We'll call this the recurrence rule.
Well, I think this will become clearer if we take a look at a specific example. Let's find the rook polynomial of this configuration. The square with the rook symbol on it is the one we choose for our recurrence rule. The equation we get is this. The first term arises when there is no rook on the chosen square. The second term arises when we put a rook on the chosen square and eliminate the row and column. If we now apply the product rule to each term, we get this. We now know the polynomials for each term, So we get this. After a little algebra, this just becomes 1 plus 5x plus 6x squared plus x cubed. Well, now we come to our final device, which is a theorem, very much like the principle of inclusion-exclusion, which you met in section 9.4. This theorem applies in any situation where you want to arrange n rooks on an n by n board, avoiding certain prohibited squares. Here we've got the squares, prohibited squares shown in white. Now we'll usually have relatively few of those, or at the very least we suppose we can actually find the rook polynomial of these prohibited squares. So suppose this is it. Well, R0 is 1 and we don't know what the other coefficients are. Now the idea we're going to use is to start with all the arrangements on non-taking rooks. So we include all arrangements, including those using the white squares, and then exclude the ones we don't want. Well, this diagram I've got here will help me to explain the argument to you. It looks a bit like an onion, and it's got various layers, and the layers are numbered. And what these numbers mean, they refer to the number of rooks on prohibited squares. So what I actually want, of course, is this outer layer where there are no rooks at all on prohibited squares. The snag is that when I start, the only thing I know is the total number of arrangements, which is n factorial. So what I'm going to try to do, having included the things I don't want, I'm going to try and exclude them again. Well, how many ways are there, how many arrangements are there in which there is at least one rook on a prohibited square? Well, first of all, how many ways can you put a rook on a prohibited square? Now, this is where we need the rook polynomial, you see, because the first, or rather second coefficient, R1, tells us that there are 1 ways of putting one rook on a prohibited square. What about the other n minus 1 rooks? Well, they've got n minus 1 rows and columns, and so we can permute them as we like and get n minus 1 factorial arrangements. So altogether, we're going to subtract R1 times n minus 1 factorial. Now, the snag is, of course, we can't count. Because if you think about it, look at the arrangements with 2 rooks on a prohibited square. Now, these things, we've included them once, but we've also now excluded them twice, once for each of the rooks. And so we must add them back in once more to get rid of them altogether. Now, how many ways are we going to add in? R2, because that's the number of ways of putting 2 rooks on prohibited squares. The other n minus 2 rooks gives the n minus 2 factorial. And we continue like this, alternately adding and subtracting things until we finally reach the total theorem.
Okay, so we've now set up all the results we need to find a rook polynomial for a general set of squares. So let's return to our original jobs problem. There are fewer white squares than black squares here, so we can try our theorem. First, we have to find the rook polynomial of the white squares. We can use the product rule by dividing up the white squares into 2 sets. We can then pick one square in each configuration and apply the recurrence rule. The pink diagram gives the upper of these 2, and the green one gives the lower 2 configurations. And now all these 4 configurations are similar to boards that we've already analysed. So we get the following polynomials. Collecting all the terms together, we get just this. And we can now use these rook polynomial coefficients in Roy's formula. So in this formula, I must put n equal to 5, and this will give us, applied to our rook polynomial, the total number of configurations. If we evaluate these factorials, we'll get this, which simplifies to a single number, 12. So that's the number of ways of distributing the jobs among 5 people. And you can see that the rook polynomial technique, although it's a bit cumbersome for 5 people, is really quite general and would come into its own for larger numbers. Well, finally, to show you that this technique is more versatile, we'll have a glimpse at one other problem called the problème de ménage. In a dinner party involving 3 couples, one thing we can notice is that if we wish to seat, say, the ladies so that they're not sitting next to their husbands, and men and women are sitting alternately, there's only one way of doing this. But if we increase the size of the party, the problem becomes less simple. Good day, gentlemen. Here we're preparing a dinner party for 5 couples. How many ways are there that we can seat our wives in alternate seats round the table so that no wife is sitting next to her husband? Well, let me show you how I'd work it out. I'd need to have 5 columns, 1 for each lady, and 5 rows, 1 for each seat. Now, I wouldn't want to seat my wife in seat number 1 next to me, so I'll put a mat on the table there to show that that square's prohibited. I wouldn't want her in seat 5 next to me either. And for my first guest, I don't want to sit his wife in seat number 1 on this side of him, or in seat number 2 on the other side of him. And so on round the table. For every lady, there are 2 seats that we don't want to sit her in. And to find out the total number of ways of seating the ladies as we want them, we'd need to find the appropriate coefficient of the Root polynomial for the white squares. But there are fewer green squares than white ones, so we'd use Roy's theorem to work this out. This problem, in fact, turns out to be very similar to the jobs problem. Have a go yourself at solving it after the programme. We've given you the solution in the broadcast notes.
I'm sure you realise by now that counting isn't always child's play. Many enumeration problems are extremely difficult, even impossible without special techniques. Now, Root polynomials are just such a technique, and I hope we've shown you that they are useful in quite a wide variety of different situations.